Alright, so here we're going to calculate or figure out how to measure the power consumption of this ignition control module. So first, I've written down basic Ohm's law, voltage equals current times resistance. And then the power consumption is the current times the voltage, the potential across that resistor. Now to derive this, maybe I'll do a separate segment on, starting from the fundamentals of charges, the electric field, how charges are, what the force is between charges, and how to define this electric potential. Okay, but in this case, all we need are these two equations here. And then first let's take an example of just the 12-volt battery and some resistor and figure out what the power consumption is of that resistor. So to get our power consumption, we need to know two of the three variables here: voltage, resistance, and current. So it depends on what's easier to measure. Usually in an operating system, it's the easiest to measure voltage with a voltmeter, and then your current with an amp clamp, for example. So in this case we would use the first equation here, power equals current times voltage. So in this case, so let's take for example a fuel pump. Typical modern fuel injection, fuel pump, current is about 5 amps, and our voltage is always system voltage, let's just say 12 volts. So when that pump is running at these parameters, our power consumption would be 5 amps times 12 volts. Okay, equals 60, and the units for power are watts. Okay, so that's pretty familiar. You can think of a 60-watt light bulb, or a watt is joule per second, so it's energy per unit time, or work per unit time. Okay, and again, the units here might not be really obvious, but you can derive from amps and volts how to convert to joules per second. So very simple calculation. Now we need to see how we can apply this to our ignition module. So let me draw that up and we'll see what data we need to collect to get our consumed power. Okay, so let's figure out what data we need to collect to figure out the power consumption of this ignition control module. So here's the basics of the ICM. So inside we have a little logic board, and which controls the power transistor, okay, to cut the current for the primary winding in our ignition coil. And out here is the input, the camshaft position sensor, in this case the little reluctor wheel, CMP. So we need to figure out what in here consumes power. So first we have our logic board. It has a power and a ground. So anything that has a power and a ground, if there's any current going through it, it's going to consume power. It doesn't have to be a resistor or a motor. So what measurements do we need to take advantage of our formula here? So we need current and voltage. So on this leg of the circuit, first we're going to measure current around that wire. So this is going to be our first current measurement. Then also we need to measure the voltage on this wire. So from here, voltmeter to ground. So that's V1 and A1. So P1, the power consumed by this logic board, will be simply I1 times V1. I guess to be consistent, we'll mark that as I1. So current and voltage. Now the second component in here that can produce power is this the power transistor, controlling the current for the ignition coil. Now ideally, you know, what we're taught is when this transistor turns on, the voltage in this leg drops to 0, right? And according to our formula, even if the current is really high, if the voltage is 0, our power consumption in this transistor will be 0. Obviously the ignition coil, you know, if there's 12 volts across the ignition coil and there's current flowing through it, there would be a lot of power dissipated here. And we can, you know, calculate that. 5 amps through the coil, 12 volts across the coil. It's actually the same as for our fuel pump example, so about 60 watts. Again, not constant, only when it's being pulsed. But this transistor isn't perfect, okay? You know, when it turns on, this leg, I don't think will drop to 0. And that's very key. So we still have to take a voltage measurement, V2, let's call it that, to ground. And we'll take a current measurement, call it I2. So the power consumed by just that transistor will be I2 times V2. Alright? And that's it. There's nothing else in here that can draw any power. So our total power consumed, P total, will be P1 times P2. And this will be, you know, we'll figure out how many watts on average that module is consuming. So let's go out to the car, collect some data, and come back for the analysis. So now what we want to do is measure the power consumption of the ICM that lives inside the distributor here. So here's a setup. There's a distributor, obviously. The ignition control module lives inside of here. Here are the wires coming to it from the ignition coil. Okay, pretty straightforward. Now the wires in the ignition coil, there are four wires plus the high tension lead. So this black with a white tracer, that is their main feed from a fuse. Now that feeds the primary winding in the coil. Okay. The white wire next to it is attached to the control wire here, the blue. So you see 4 wires, but they're actually 2 separate circuits. So this goes to our computer and our tachometer, and there's actually a little test port here. So that's how our tach works. And then the second connector, that's the conduit that goes to our distributor. The black wire here with the white tracer, that's the power feed to the ignition control module to make the logic, you know, the little board in there function. And finally the blue wire is the control for our primary side of the ignition coil. So that's the wire that's going to carry our primary current. You know, the transistor in here is going to turn it on and off. So in this case, the 2 wires that we're interested in are the ones that go to the ICM. So first what we're going to do, since we're interested in power consumption, is measure the voltage drop and current flow at the same time on each wire separately. First we'll do the one that powers up the logic, the board, and then we'll do the one that is actually the primary coil current. So we're going to do 2 channels simultaneously. Channel 1 is going to be our voltage drop. Okay, so there's the lead back probing the wire there, and my ground is on the distributor body since we're interested in the voltage drop, basically across the ICM. So that's the easiest place to connect it. And then our current clamp, let's turn it on, re-zero it, is going to measure current this way on that black wire. Alright, let's set up our scope. Let's see here, 20 amp scale. Make sure our probe is connected here. So the ground for the probe should be connected to the common ground, obviously. So we connect that. Alright, so scope is set up. Now I'm going to fire it up, and what do we expect? Well, I expect the voltage should be at system voltage. That's fine, and the current, well, I don't know how much the current the logic board will draw, but I'm assuming not much, less than an amp. But let's fire it up and see what we see. Alright, so here we have our 2 traces. The voltage is at about 13.3, which is normal system voltage, and our current trace looks like about 0.02 average. There's some spikes in there, but on the scale here it's about 0.1. We can round it off, but very small current. Average current going through that wire feeding the logic inside the ICM. Alright, so let me save this waveform and we'll go to the more interesting one, the control wire for the primary side of the ignition coil. Alright guys, we're doing a measurement here on the ignition coil for this power consumption calculation. Now, I'm on the first wire on the voltage trace. That's just the feed wire to that ignition control module circuit board. So, this black for the white tracer. And our voltage, now the Verus is having issues. The calibration is off. See, it's showing 16 volts as system voltage is actually closer to 13. But we're going to have to ignore that for now. Now you see the drop in voltage right here, that's when the ignition coil, the primary, is being turned on. So the voltage in that circuit is actually dropping just because the coil itself is drawing current. So that's normal. Now for the current trace, we have our amp clamp, and on the first measurement, well, let's see, I have it re-zeroed. Press the 0 button, we're at 0 amps, put it on this black wire, and check that out. We have like a half an amp, negative half an amp, so the current would be going back into, supposedly from the ICM, back into our feed. Now, that was very strange. I couldn't explain that until I thought, well, we're using an inductive amp clamp. And what does it measure? Well, it uses magnetic field to calculate the current. Now see, I moved that around, and look what happens to our trace. And if I turn this clamp 90 degrees, look what happens to our current. It gets positive. Turning it this way, negative. Positive, negative. So the lesson here is you have to be really careful using an inductive amp clamp near a device that produces a high magnetic field. So now we can safely say that that is kind of a ghost amperage. It's not real amperage going through our wire. It's actually just a clamp picking up magnetic interference. Now we can even experiment with this. I mean, see, there's no wire. I'm bringing it close to the coil. And look what we get. Wow. So in this case, we have to ignore that hump. Now, let's re-zero it. All I'm interested in is the current, the actual current on that wire. So what I'm going to do is re-zero it, put it on here, and we're just interested in the steady state value. So 0.13 amps. Now let's turn the key off, key on, engine off. Constant rage, the CD is stuck in the player. So our clamp is off. Clamp is on. Now let's turn the key on. .11. Okay, that's the value we're going to use for the current on that black wire. So we're going to move our probes right next door to that blue wire. I'm going to re-zero my amp probe just in case. Okay. Alright, cool. Now we see our current ramps. Let's drop the time base. And obviously we're seeing significant amperage. So there's one current ramp. It's when the transistor turns on, there's our voltage drop. So that's what we're interested in. When the transistor's off, there's no current, so there's no power dissipated inside the ICM. When the transistor turns on, that's when the magic happens, you know. So our voltage is dropping not quite to zero, so let's put that on the line here, okay? So maybe around 1 to 2 volts. And then here it's actually limiting the current. Maximum current is about 5.5 to 6 amps, okay? So we have to calculate the power consumption for one current ramp. And then we have to see how often the current ramps repeat. You know, because there's this dead time between the firings, and then we have power consumption and then no power consumption again. So we have to see what percentage of the time is the transistor being switched on. So I'm going to save this again and we'll analyze it on the whiteboard. So another thing we have to keep in mind is this is at idle. if we increase the RPMs, obviously the coil is going to fire more often, and we're going to have greater power consumption. That's the ICM. So if I rev it up, see how the peaks get closer together? So we'll do our calculation, for 1,000 RPM, and to get the power consumption for 3,000 RPM, just multiply by 3. Really simple.